Hello everybody, it's time for video 4 of lecture module 4, our last video for this lecture module. I'm going to jump right in here. We're going to continue our exploration of the moon. And in this video, we're going to talk about the major surface features that we see on the moon, both large scale and small scale. And then we're going to talk about what the surface of the moon is like, the lunar regolith, this fine coat powder that's covering the entire surface of the moon. And we'll save the end of this video for a little bit of a surprise of where we can find water ice on the moon, because yes, there is water ice on the moon, which could be very, very vital information for establishing any form of human settlement on the moon. We need water to survive. We need it for rocket fuel. We need it to drink. We need it for shielding. We need it for pretty much everything. It is the most valuable space resource. So let's go ahead and start by taking a global view of the moon. You can get a shot like this with a pretty decent camera, or you can get a shot like this with an OK telescope. And you can see what the surface of the moon looks like in a little bit greater detail than you can see with the naked eye. So if we go ahead and we look right here, we will notice that there are the lighter areas of the moon, and then there are the darker areas of the moon. The darker areas are roughly round in shape. They are relatively smooth. You don't see a whole lot of impact craters on them, just a few here or there. And then compared to the lighter areas, we would maybe want to describe those as heavily cratered. If you were to look at an elevation map, you would notice that these lighter colored areas that are just covered in impact craters are higher altitude. So they are the highlands of the moon. So let's call these lighter areas that are higher altitude, covered in craters, the cratered highlands. We are very creative with how we name different regions. So we have the lunar cratered highlands. These dark regions, the regions that are darker, roughly round in shape and relatively smooth, devoiding craters. When people first started to look up at the moon and you could see the color variations and people were no longer thinking it was all that was an optical illusion, they wondered, what are these darker regions on the moon? And they thought they might be these giant dark seas. They actually thought maybe liquid water. We know that's not the case, but they still carry the Latin name for sea mare, or that would be the singular, so this would be a mare. You take all of them together and you're talking about the maria. So these darker areas are what we call the lunar maria. We can zoom in and we can see one here. Yes, quite round in shape, pretty smooth, but yes, it does have impact craters on it. This is going to indicate that it's a younger surface. It's darker in color because it's enriched in iron. So that's going to be part of the story that we have to explain of why they're darker in color. How did it become enriched in iron? And the story is going to come back around that it's not too far off to call these seas, except these are seas that are frozen lava. These were once giant lava lakes that then solidified. All right, so let's take a look in words rather than pictures. So we have the two dominant surface features, and that's how I'm going to try to, when there are large scale surface features that have names for planets, I'm going to call them the dominant surface features. The major terrains is another phrase I'll throw around. So we have the lunar maria. I know it looks like Maria, but it's pronounced Maria. Singular is mare, and that is the Latin word for seas. So these are the smoother, darker regions. They have lower elevations, and they're sort of giant basins. They're roughly round in overall shape, and they are young compared to the highlands. And how can we tell that? They have fewer craters. The surfaces have been exposed to outer space for a shorter amount of time, so they've accrued less impacts on their surface. And they're darker in color to an increased iron content in the rocks there. Contrasted to that, we have the other major terrain of the cratered highlands. These are mountainous, so yes, lots of mountains on the moon. And this area is just covered in craters. They're lighter in colors. The fact that they have so many craters tells us that they are older than the Maria. They are on average several kilometers above the Maria, so they truly are highlands. And if we look, these dominate the far side of the moon. Yes, on the near side we have Maria and cratered highlands, but on the far side, we have very few Maria and almost all cratered highlands. Remember, we didn't get to see this until the space age. And boy, were we surprised when we finally got to see the far side of the moon, not the dark side of the moon. Sorry, Pink Floyd, the far side of the moon. And yes, the far side of the moon, when we have the new moon, when the face of the moon that we see is shrouded in night, the far side is in complete daylight. So the far side is not the dark side. It's just the side that's farther away from the Earth that we can't see. But we were very surprised whenever we saw it. We're quite familiar with the near side where we see the Maria. And if you can see a man in the moon, then good for you. I've never actually been a big fan of the man in the moon kind of thing because I've never really been able to see a man in the moon. But you have the Maria and then you have the cratered highlands. You go to the far side, yeah, there's like a little Maria here. The South Polar Aitken Basin is sort of a Maria, but not quite like we see on the near side. It's pretty much entirely cratered highlands. So there are very two different faces of the moon. The near side with Maria and cratered highlands, and then the far side, which is almost all cratered highlands. Whenever we have a dichotomous appearance like this with a planetary body, and in this case, it's the near side of the moon is dichotomous to the far side of the moon, we call this the near side, far side dichotomy. And dichotomy just meaning two separate things that are different. So we have the near side, far side dichotomy, but everywhere, both in the Maria and in the cratered highlands, we notice that the moon is covered by craters. So if you want to talk about what is the feature that you would first pick out about the moon is covered in craters. It doesn't have an atmosphere, so it doesn't really have any sort of erosion processes like Earth has, and it's been sitting around since formation about 4.4 to 4.5 billion years ago. So every time that something from outer space hits it, it's going to create a impact crater. So it's going to create one of these bowl-shaped depressions. So something from outer space comes and impacts the surface, leaving behind a bowl-shaped depression with a raised rim that we call an impact crater. So here you can see impact craters here, and these are going to be the dominant feature we see on every airless body in the solar system that has no sort of geology going on, so no forms of erosion. So this is also going to be the dominant thing that we see on Mercury as well. And craters come in two different kinds, simple and complex craters, and this depends on the size of the impactor, whether you're hitting it with, say, something the size of a golf ball, if you're hitting it something like the size of much, much, much larger. So simple craters, highlighted here on the left, and the crater Torontus H is 8.5 kilometers from side to side. Yes, this is considered a small crater on the moon. So these are the smaller, and they're very round. They have raised rims, and they look like a nice bowl-shaped depression. On the moon, they are always 15 to 20 kilometers or smaller, all the way down to the meter-sized. So even the small craters end up looking like these simple craters. And whenever I mean small, I'm talking about like meters to tens of meters small. Contrast those to what we call a complex crater. These are much, much larger. So here's Tycho crater, a famous crater on the moon, which you can see with binoculars or a small telescope. Here you can see that it is still round in shape, but it's not a bowl-shaped depression, it's flat bottomed. And you have these concentric rings of mountains, and here in the center, you have this central peak that sticks up. And that actually occurs during the impact that creates it. It sends out a shock wave going down, seismic waves, that then reflect back up and push up a mountain peak. If you're interested in how craters form, it's a very detailed process. You can ask me for more information and I can provide you with some more, and I have some information in the supplemental slides. But the complex craters are essentially the large craters, simple craters are the small craters. So if you're greater than 15 to 20 kilometers diameter, you're going to be a complex crater on the moon. And this has to do with the energetics. The size, where you have the cutoff between simple and complex craters, has to deal with the surface gravity of the planet. So we would have to modify all this. We get simple craters and complex craters here on Earth, but we have a higher gravity, so the change is at a smaller size. Those are details that you don't need to remember, but since we're here, I might as well share as much about planetary astronomy as I can. So since the moon doesn't have an atmosphere, we can use the same for Mercury, it introduces and becomes an ideal test case for us to develop ways of dating surfaces. Because we want to know how old the surfaces are on things, because that's going to be an integral piece of information for understanding how they go from their initial state, their protoplanet state, or their planetesimal state, all the way to the state that we see them today. So the moon has been sitting around pretty much unaltered for the past 4.5 billion years or so. And every time something comes and plunks onto the surface, it adds an impact crater, either simple or complex. And we have a decent, actually, I shouldn't say decent, we have a very good constraint on how often things should be struck by what size of impactors. So we know how often new craters should be formed, which allows us to start doing some dating techniques. And let's go over some of the basics. Let's do just simple crater counting. We have two surfaces. We have a brand new fresh surface, and then we have a surface that's been sitting around for, say, 4 billion years. The fresh surface will have no craters. It's had no time for something to impact it yet. The 4 billion year old surface has been sitting around for 4 billion years, just being impacted over and over and over and over again. It would have a whole lot of impact craters. This gives us one of the basics of crater countings. More craters means older. Less craters means younger. So pretty simple, more craters, older. And if we actually know the impact rates, we expect craters of this size this often, then that gives us not only like, hey, this surface is older than that surface, but we get an idea of like, oh, well, this surface is millions of years older than this surface, hundreds of millions of years older than this surface, or billions of years older than this surface. Another thing that we can use is called the law or the principle of superposition, which is the younger material is on top. So let's imagine we form ourselves an impact crater, and then something happens, some geological event happens, which creates a cliff inside that impact crater. So you have the impact crater, and then you see a cliff running through it. Well, what had to form first? Well, you had to form the crater before you could form the cliff that went through it, telling us that the crater is older than the cliff. What is on top is younger. So let's quickly look at the Maria here. So here we have the Maria, and here's an impact crater in the Maria. Well, you had to form the Maria first so you could put an impact crater in it, so you could strike the surface of the Maria. So this crater is younger than the Maria. And we call that the law of superposition. What is on top is younger. So relative ages, that's great. We can say this surface is older than that surface. Maybe you narrow it down to a couple tens to hundreds of millions of years older or younger. But we really want to know what is the age of the surface. We want an absolute dating method, not just a relative dating method, an absolute one. So how can we take this crater counting idea and then link it to something where we actually know the dates? How can we say, oh, look, here we have a few craters. This is our young surface. This one has more craters. It's older. This one has a whole bunch more craters. This is the oldest. And then actually give dates. Like this is 4 billion years old. This is 3 billion years old. And this is 2.2 billion years old. Well, luckily, we've been to the moon. So take that, conspiracy theorists. The astronauts went up there, they collected 400 kilograms of wonderful lunar samples. And if we were in class instead of on video, this is the day that I would actually bring a moon rock for you to hold in your hand and check out, returned by the Apollo 17 astronauts, just so you can see we really do have these things. And we can do radioactive isotope dating on all the materials that are brought back from the astronauts. They visited the Highlands, they visited the Maria, they visited several locations in each. So we can now actually date those surfaces on the moon. We can then count up the craters that we see on those surfaces. We know that those surfaces are that age by the samples brought back by the astronauts. And now we have a way to link the number of craters, the crater counts, to an absolute age. This gives us a method to calibrate the ages of all the surfaces in the solar system. We know the impact rates well for all of the solar system. And now we can use the moon as our linchpin, our cornerstone of absolute ages. So anytime we talk about the ages of surfaces in this class, it's all going to come back to this right here, that we have lunar samples that give us an absolute age of certain surfaces on the moon, which allow us to turn crater counts into absolute dates. What do the absolute dates come out to be? Since we have all of this, we can start looking at the moon and we can already see some pretty amazing things that are telling us the story of its formation and evolution. The cratered highlands are about 4.4 Gya, G-Y-A. Okay, it's not really Gya, although it's fun to say it that way. Gya means giga years ago, billion years ago. So 4.4 billion years old. We look at the Maria, and depending on which Maria you're looking at, they all have a different number of craters on them. And they age, or they range in age from about 3.2-ish to about 4.1 giga years ago, billion years old. So the Maria were forming over a period of time. This period of time also coincides with that piece of evidence that we use to understand the formation of the solar system, the late heavy bombardment. You remember the moon and Mercury record the evidence of a late heavy bombardment. So now we can actually determine when that was occurring in the formation of the solar system. That was about 3.9 billion years ago. Notice that these numbers overlap. That is not a coincidence. Those two ideas are going to be linked together. So now we have a way of determining ages of the surface, which is going to be critical to understanding the evolution of planetary surfaces. But we aren't done. We have just talked about craters on the surface of the moon, but what would it actually be like to be an astronaut and you land in your pod and then you hop out? What do you expect? And we actually did not have that great of an idea of what to expect, other than we were a little bit concerned. Through a variety of other methods, we had already determined that the surface of the moon should be covered in this very, very, very fine-grained dust layer of little tiny microscopic rocks. How microscopic? About 10 microns on average. That's about a little bit thicker than your human hair on average. So this fine-grained rocky layer, we give it the Latin name for fine rocky layer, regolith, a fine-grained rocky layer. What creates this fine-grained rocky layer? We talked about large impactors creating simple craters and complex craters, but there is a constant rain of very, very small micrometeors, like tons and tons and tons of this material rains down on Earth every day. It rains down on every surface in the solar system every day. Things that are sizes of pebbles, all the way down to things that are the size of grains of sand, to things that are just a few microns in size. But they're impacting with at least the escape velocity of that planet. So there's this constant rain of materials, these small things, hammering into the surface of the moon. Each time, the fact that they're moving at tens of kilometers per second, or up to tens of kilometers per second, they might be small, but they hit with a lot of force. Bullets are small, but they hit with an incredible amount of force because they're moving incredibly fast. These things are smaller, but they're moving orders of magnitude faster. So each time they hit the surface, they break apart the rock that's on the surface, grinding it down to smaller and smaller and smaller. This constant rain of micrometeoric impacts grinds down the surface of airless bodies, including the moon, generating this fine-grained rocky layer that we call regolith. This is what the astronauts left their footprints in. And based on this general process, we didn't know how deep it was going to be on the moon or how structurally sound it was going to be. Will the landing module just land and sink into it? Just hope not. Well, turns out it didn't. Okay, the landing module is fine. Whenever the astronauts hop out, are they just going to sink down into it and be trapped like quicksand? Turns out, no, you can walk on it. They left their footprints in it. We now know that the average depth is a few tens of meters deep, all the way to maybe a kilometer deep, or much, much as we get to the cratered highlands, which are older and had this process of generating regolith going on longer. Let's take a look. So this is a pretty large regolith grain. You can see they're very jagged That's evidence of how they're actually forming, because micrometeor impacts are just going to shatter things, leaving lots of jagged edges, no other erosion to smooth out those edges, which means that this stuff sticks to everything, including the lunar buggy, the uh, suits so they can walk around on the moon, the lunar module. It got on everything. It turned off the buggy, it ruined the buggy, they had to fix it. They were starting to drag that into the actual lunar module, and if you breathe this, you can imagine sharp, jagged things going to the lungs. It's not very good for humans, plus all the other things of all the chemical reactions that are going to happen as this oxidizes. It was a pretty bad thing going on there. We now have ways of dealing with it, but it turned out relatively okay for the astronauts. You can see they've dug around in the regolith right here. Here you can see tire tracks in the regolith. You can see all the footprints in the regolith. You can see the effect of the regolith sort of eroding away the edges of this crater in the background. You can see that the moon does have mountains. And then, of course, the famous Neil Armstrong's boot print from Apollo 11 right there is pretty much almost immortalized on the surface of the moon. So we have the constant rain of micrometeor generating the regolith. They have very, very jagged shapes that builds up over time. So this does provide a very, very, very slow erosion process on the moon, a lunar erosion process, this generation of regolith, this constant rain of micrometeoric impacts grinding up the surface. And we know that this is going on because there is less than we expect craters that are 20 meters in size. Given that we don't really see craters that are 20 meters in size, less than we expect, they've been eroded away by this generation of regolith, this micrometeoric impact, making regolith effect. That actually gives us an erosion rate of about 5 meters per billion years. That's about 1/100,000th the erosion rate of Earth. Another way to put it, it makes a little bit more sense to me, and also it's a whole lot cooler. That footprint, this one right here, that will survive for several million years before this erosion process destroys it. So if you want to leave your mark for millions of years, all you have to do is go up to the moon and put a footprint, put a handprint. Anything you leave in the regolith, any print will last for millions of years. So that is a very, 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 very slow erosion process. But if we're going to talk about airless bodies, bodies that don't have atmospheres like the moon, Mercury, large asteroids, this is going to be the dominant erosion process, is this generation of a regolith. And now, an interesting question. Is there any water on the moon? If we go there, can we fill up an Nalgene with nice, clean, liquid water? So it turns out there's zero liquid water on the moon, but that does not mean that the moon is without water. The answer is an unexpected yes. There is water in the moon, but it's water ice. Where is it? Well, let's come back to that, because let's first talk about how we can actually get water, because it's not going to be a whole lot of water. Where the water that we do find is going to be trapped within rocks. It's going to be somehow locked into the subsurface. And we know that the moon in general is very, 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 very dry. So if we were to take some of those lunar samples that we have, which we have done this, and examine them looking for water molecules, in a kilogram of that material, you'll be lucky to find more than a few water molecules. So pretty much bone dry, none at all. By comparison, you can go to the Atacama Desert. There are places in the Atacama Desert here on Earth where we've never observed it to rain, which is just mind-blowing. Pick up a rock there. By weight, 1 to 2% of that rock will be water. So the moon really is bone dry in general, but if we go to the poles of the moon, and here I have a little golf ball. It's got the divots in it. If I have a light source coming from this side, so the sun's over here, here's the poles, and the sunlight will just go over. It can never get down into these divots on the poles. It can never hit the bottom of craters at the poles, creating what we call permanently shadowed craters. they have never seen the light of day for billions of years, which means that they're incredibly cold, cold enough where if you can put some water there, it's stable and will survive billions of years. So we started to suspect that there might be water in these permanently shadowed craters. And I want to show you what these things look like. So here is an image of Shackleton crater. It's permanently shadowed. So the bottom of this has never seen visible light from the sun. But that doesn't mean that we can't probe it using laser altimeter data, so we can actually map out what this looks like, or we can look in different wavelengths, and we can even do spectroscopy of the materials that are down there, things like that. So we can start assessing what's going on in these permanently shadowed craters. So here you can see the permanently shadowed part of the Shackleton crater. So we suspected there might be water ice in these permanently shadowed craters, so we had a rather interesting idea to test whether it's there or not. They're locked in the bottom of these deep, dark pits, so how can you actually see the material there? Well, why don't we just loft some of it up above the crater rim? So during the launch of the Lunar Reconnaissance Orbiter, LRO, stage 2 of the rocket had its own little rockets, so it was directed to impact this crater right here, Cabeus crater. So we wanted to go ahead and hit this with the stage 2 of the rocket. We were on target. So the stage 2 hit inside that permanently shadowed crater, it lofted a bunch of materials as it formed its own little tiny crater within the crater. We looked at the plume of material that's coming out. We analyzed it spectrally, and lo and behold, we see the spectral signature of water. So yes, Cabeus crater has water ice within it. We can also, or since then, there have been other missions that have been launched to the moon. The Indian Space Agency is a mission called Chandrayaan-1. NASA had an instrument on it, a near-infrared spectrograph, perfect for detecting water. It was called the Moon Mineralogy Mapper, or M-cubed, MMM. So it can actually look for the spectral signature, the absorption features for water. And as it went over the South Pole where that Cabeus crater is, then it mapped out, and where you see blue right here is where it detected water ice. There are a few other lines of evidence. You can go look at them in the supplemental slides. But yes, we have positively detected water ice on the moon. Where is it? It's in the permanently shadowed craters at the poles of the moon. They have to be at the poles or else they won't be permanently shadowed. The question remains, how much water is there? Well, there's less water there than the driest desert. So those rocks in the Atacama Desert have more water within them than even in these permanently shadowed craters. It's about 1 part in 100,000 at maximum of how much water is there, which sounds like that's not very much, except we're really, really good at potentially harvesting this, and then we can get the water out of there, which is the most valuable space resource that we can have. It serves to keep humans alive. It can be used as radiation shielding. It's very good radiation shielding. It can be used to make rocket fuel. If you want to set up any agriculture, you're going to need water. Water is the space resource of space resources. It makes every other resource look not important. And water is expensive to get to outer space. Based on current estimates, Elon Musk and NASA are now bringing this cost down. But right now, to launch about 1 liter of water to the moon, to launch that much water, 1 Nalgene's worth of water, costs somewhere between $10,000 and $100,000. And I don't know about you, but I would need more than this to survive. A settlement's going to need a lot more than this. So we are actually targeting these regions to set up our moon settlements, so we can actually harvest this water, and even though there's not very much, we can still gather it and then save a lot of money and actually make it feasible to perhaps create lunar settlements. All right, that ends lecture module 4. Thank you for tuning in, and I will see you for lecture module 5, where we'll continue our story of how the moon formed and how it evolved, and then launch into Mercury and Venus.